All right, so today we kick off the whole title of this chapter is States of Matter. Okay, so we take a little time and we describe how specifically are we going to describe the states of matter. And so we start out here with this kinetic molecular theory. And I abbreviate this quite often as just KMT. And so you'll hear me say the kinetic molecular theory. And what happens is this. This was a theory initially used to explain how gases behave. And then they said, okay, we could probably apply that same exact info to solids and liquids. And so it becomes, how do atoms, how do molecules, how do compounds behave when they're in each state of matter? Because they do behave differently, okay? We take a couple of things here and we make some assumptions. So throughout any theory, right, the reason it's a theory and not a law is there's some things either A, we don't know, or some things B, we have to assume. We don't quite know if that's true or not. Okay, so we take a look at particle size, their motion or movement, and then their energy. Okay, so any questions here? Does anybody still need it? All right, so the first thing that we're going to look at here is our particle size assumption. It says here particles are really, really small. Remember, this is first initially describing that behavior of a gas. And so really, really small. Okay? Now, the best way to explain this is through the picture. These little green spheres represent the actual size of some gas they picked out. Everything else is empty space. So there is a lot more empty space than there is to our particles. So the size of our gas, in this case, is really, really small compared to the size of the container that it is in. And there is empty space. Now, just because these things are really, really far apart, they're really not going to interact a whole lot with each other. They're not going to push and pull. And that is one major assumption we have to use as we go through this particular process. Questions? Does anybody need it? Next assumption here is our particle motion or movement. It states that a particle, and particularly a gas atom here, because that's how they initially described the kinetic molecular theory, is in constant motion. It is constantly moving. Because what happens if a particle stops moving? We would actually get to this concept called absolute zero. And to be honest with you, we have not ever reached absolute zero. We've gotten close. We know that it's very, very cold. It's negative 273.15 Kelvin, but we actually haven't got down to absolute zero. And so their thought process when it gets to absolute zero is some things that we know about physics are going to start to break down. And they do even at those cold temperatures, but we'll get to that business more with our gases. Okay. Now, one thing that we have to emphasize here are collisions, right? When they smack into each other, the particles, and you can see the particles smashing in with the picture here, they're completely elastic, right? So let's think what it means to be elastic. If you stretch out a rubber band and you let it go, what happens to it? What's that? Snap back. I like how you said that. Goes back to its original form before you stretched it out. Same thing with the particle hitting each other. We assume in this theory they hit each other, they bounce off each other, and they perfectly go back to the way they are before. In reality, there's actually some energy exchange, energy given off in some different forms, but we assume that, hey, it is perfectly elastic. And that's what we mean by having elastic collision. Questions? Anybody need this? All right. So we talked about particles that are moving. We can now talk about the energy associated with moving particles. So remember, all matter takes up space, has a volume, and in this case here, is going to have a mass. Well, it's moving. Another term for moving is velocity. Velocity is movement with a specific directions, right? So the atom could be moving towards the parking lot. The atom could be moving towards the back of the wall. Keyword, it's moving, and it's moving in a certain direction. We can apply this simple physics formula of kinetic energy equals half times mass times velocity squared. Now, we don't do any math, but that is our math formula that is associated with this. And remember, gas. Yeah, they're not very big. There's not very many gas particles if we had a container of oxygen, a small container of oxygen. However, there's some mass of that oxygen. They are moving, and as a result, we can calculate that kinetic energy. The major thing here that we take away is temperature. Temperature says it is the measure of the average kinetic energy of all particles in your container in your component. So think for a moment. If particles are moving really, really fast, do you assume it will be a hot temperature or a cold temperature? Hot, right? There's more movement, more energy, more kinetic energy, and so hotter that sample size is, or that sample is. Okay? Questions? Does anybody need this? Okay? All right, so we're not going to watch all of this, but I do want to emphasize a couple things. We'll see if I can't get this to play here. This is a pretty good video, at least the first part is, explaining what is the difference between solid, liquid, gas. So far, we've just talked about gas, but what is the difference? And specifically, how could we apply that kinetic molecular theory? So we'll watch a few minutes of this, and then we'll be finished out with section number 1 here. So hopefully this plays out. It might be...
Kinetic molecular theory. Kinetic molecular theory is a scientific theory that is used to describe the states of matter, solid, liquid, and gas, and how they transform into one another. In this lesson, we're going to visualize solids, liquids, and gases at the molecular level. We're going to describe solid, liquids, and gases based on their shape and their volume. And then finally, we're going to use kinetic molecular theory to understand ideal gases. Each video in this series is going to help us better understand gases and how they behave under certain conditions of pressure and temperature. Kinetic molecular theory is going to lay the groundwork for our understanding of gases. So let's begin with a definition of kinetic molecular theory. It really has 2 parts to it. The first part says matter is made up of particles, and then the second part says the particles are always moving. Now this goes for all matter. This little animation here would be what a gas looks like. The molecules or particles are spread out and they're moving pretty rapidly. Now this theory is going to describe the amount of kinetic energy that these particles possess. And so we have to understand what kinetic energy means. Kinetic energy is the energy of movement. And so the more kinetic energy a particle has, the faster it will move, and the less kinetic energy it has, the slower it's going to move. And we know that these particles are called atoms and molecules. So that's kind of the groundwork before we move on looking at solid, liquids, and gases. So let's start with solids. And what we want to do here is zoom in on the particles of a chunk of matter. Let's say one of these ice cubes here, this glass of water. So if we could zoom in on these particles, we could see kind of what they're doing. Now the molecules of water are just represented by these little tiny spheres here. And they would just be kind of vibrating in place. They're moving slowly because they only have a little bit of kinetic energy. So solids have a low amount of kinetic energy. And one thing we have to remember is that every particle is going to have some degree of attraction with the other particles. And so they have to be moving fast enough in order to break away from the other particles. Now we call these attractions intermolecular forces. And that means the forces of attraction between molecules. So let's describe these particles in the solid chunk of ice. They're in a nice ordered pattern, and we would call this a crystal structure, or in other words, a crystalline structure. That just means there's a nice pattern to the way that they're organized. Solids also have a definite shape. In other words, if we were to drop an ice cube into a glass of water, it's going to retain its shape. It's still going to look like an ice cube. We could also say that the volume is definite. We could measure the height and the length and the width of this ice cube, but we could calculate its volume. So the volume is going to stay the same. So let's recap what we've learned about solids. The particles in solids are going to have a nice ordered pattern. The particles are going to be vibrating. They're moving slowly because they only have a small amount of kinetic energy. They have a definite shape and a definite volume. Okay, let's take a look at the particles of a liquid. This time we're going to zoom in on the liquid water here and look at what its particles are doing. In a liquid, the particles have much greater kinetic energy. They're going to be moving a lot faster. Now, they are randomly moving, so they don't have that nice ordered pattern, but they're not moving fast enough to break those attractive forces. They have the ability to flow past one another, and liquids are not going to have a definite shape, and so they're going to conform to the shape of the container that they're put into. I mean, you could pour a glass of water into a different shaped container, and it's going to fill that container and take on its shape. They do have a definite volume, and so we could use a measuring cup to measure the volume of a liquid. So let's recap liquids. Here's what we've learned. The motion of the particles of a liquid is going to be random. They're moving faster, they have more kinetic energy, and so they're able to flow past one another, but they don't have enough kinetic energy to break those attractive forces. They have an indefinite shape, which means they'll take on the shape of their container, but they do have a definite volume. Finally, we'll look at the water vapor, the gas state. And we'd have to boil the water and kind of zoom in on those particles and see what they look like. The particles of a gas will be moving very quickly. They're moving so quickly that the attractive forces really have no effect. They're very, very spread out and moving very randomly. Gas particles don't have a definite shape. They're going to fill the shape of a container, just like a liquid. And they don't have a definite volume either. We can compress a gas into a smaller volume or let it expand to fill a large volume. So to recap what we know about gases, they move randomly and very, very quickly. They're so quick that the attractive forces are almost non-existent. They have an indefinite shape and an indefinite volume. Now, the rest of the lessons in this series are going to focus.
All right, so pretty good video. I know it's a little boring there, but it talks really, really well about different states of matter, how you can apply the kinetic molecular theory to that. Any questions over this information from section 1?